All right, we're live. What are we? Saturday or Sunday? We're Sunday today. All right. Today I'm with my guest KJ. I met KJ at NVIDIA last year, and today we're gonna learn Transformers. Right? That's the plan. So I think you and I both kind of learned Transformers.
Yeah, I took a course on it back in the day, but I
With
forgot
the yeah,
everything.
I forgot everything. I like kind of remember the structure of like attention and everything. Or actually, I don't remember attention. I just remember this diagram, but like I don't really remember what it does. So there's I think two good videos that I saw. So there's like the 3 blue 1 brown. So we can watch this one, and then there's another one. What's her name? Machine. No, it's not Machine Learning Talks. It's diffusion. Yeah, this girl, Letitia, and she did a LLM lecture. Explain tokenization, transformer layer, attention. I think she's pretty legit too, right?
I haven't heard of this channel before.
You haven't heard of the channel?
Yeah.
She explained like, when the diffusion policy was very hot, or there was transformers for like images. She would explain these. Foundation. Transformer explained. BERT. What GPT-2 DALI. Oh, wait. And then like swing transformers. Swing transformers. Okay, but we're watching 2B 1B.
Yeah, I think that's a good place to start.
I might take notes.
Insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation to what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript. This sentence comes from a model going the other way around, producing synthetic speech just from text. All those tools that took the world by storm in 2022, like DALI and Midjourney, that take in a text description and produce an image, are based on transformers.
Diffusion policies don't use transformers today.
I think so. The diffusion architecture does use transformers within it, if I'm not mistaken. But it's not core to its idea. Yeah, like it doesn't require transformer necessarily, but the unit model that they did use had attention in it. Since it did kind of use it.
So like this one. But this is diffusion, right? Oh, this is not diffusion at all. Zero shot text to image. This one not diffusion based. This one doesn't use diffusion. DALI 2.
Yeah.
And then transform. So they have both.
No, that's from the related work section though.
Huh?
That's in the related work section, right? Or that method? No, you're right. Never mind.
Training details. It is a transformer. Why did they capitalize transformer? Back when like transformer was not. I don't know.
Even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another.
Attention is all you need. 注意力就是你所需要的一切。注意力。Okay. 就是。That you sound Japanese now. 就是。还看上面的。No. 就是。就。Not 就。 Not Joe.
Mhm.
Geo.
Geo.
There's like IU. Geo.
Geo.
Joe.
Geo.
Joe.
Geo.
Joe. 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 Joe.
Geo.
就是
就是
是
就是
是
就是
是
就是
你所需要的一切。你所需要的一切。
I can't say that. It's too hard.
Focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a...
This is softmax. What's a softmax? What's the softmax formula?
It's e to the x divided by summation of e to the x, if I'm not mistaken. Where x is the output of the network, right?
Yeah, x over some. I think that's. And what does that do? Why does that work?
It's because the idea is that
As opposed to just summing like
Mhm.
x over the sum of x.
if I remember correctly, the problem is that the probabilities are like very small. Wait, no. I know the summation's done to bound it between 0 to 1.
Of course, but you can have x over 1
Yeah.
over sum of x, and that also bounds it between 0 and 1.
What's e to the small number? E to the small number isn't even.
Is 1. E to the very small number is 1, right? E to the 0 is 1.
Yeah.
E to the 0. E to the 0.1
So I think it has something to
is
do
1.
with, like...
And the negative numbers, I mean, are they negative?
No, there's no negative exponentials. Because it's...
No, but I'm saying like if your input is negative,
It's,
they wouldn't work, would it?
It's basically 0. You can try it. E to the negative.
I think, yeah, because well, negative exponents make it possible. But I'm saying like, imagine your input was like minus 0.1, minus 0.2, minus 0.3, and you just do a sum, then it wouldn't, would it really work? Oh, I guess it would kind of work. Yeah, because minus 0.1
well,
over.
probabilities can't be negative.
And also the sum of those numbers could be 0.
Yeah.
Like if you do 0.3 and then minus 0.3, and if you do the equation x over the sum of x, that'll be 0.3 over 0. That wouldn't work. But if you take a softmax, it would be e to the 0.3 over the sum of 0 e to the 0.3 plus or e to the minus 0.3, and that would still work.
Yeah.
Is that why then? KJ, you don't know what you're doing then.
I'm not a deep learning person. It's been a while since I've done
Just
deep learning.
x over.
Yeah, handles negatives better. That makes sense.
That's what I said.
Oh.
Oh my god, I just derived it.
And yeah, it's normalization.
Oh, I literally have the explanation here.
Yeah.
X equals minus 0.3, 0.3. The sum is 0, so it would. So. Do you understand the amplification?
Yeah, basically, if you think about exponential function, if you go from like, let's say you have like 2 to the power of 1 versus 2 to the power of 2, that's like 2 to the power of 1 is just, or actually, let's just do 2 to the power of 3 versus 2 to the power of 4, right? That's a pretty huge difference, right?
Alright, let's plot it.
Yeah. I mean, yeah, that's the whole point. It grows very fast. Like, the difference between so yeah, the difference between like it at like 0.1 versus 0.2 is actually quite significant, right? And so by giving it like putting it through the exponential function, it makes the difference a lot bigger. So that's what I mean by amplifying it. So that any small change in input will lead to a much bigger difference. Whereas if you didn't, then like 0.1 versus 0.2 are very close together, right? But each of the 0.1 versus each of the 0.2 are very far out. So that's why.
Really, is it true? Let's see.
Well, I
So
think
consider if your 0.1 and 0.2, their distance, their difference. 0.1 minus 0.1 equals 0.1, and then e to the 0.2 minus e to the 0.1 is going to be bigger than 0.1?
it should be, yeah.
Barely.
That's not a good example.
By passing it through.
Oh, you also have to actually like normalize it and stuff as well. Like you have to make it through, go through the softmax.
You amplify the difference. So we're just gonna confront ChatGPT about it and it will tell us why.
Okay. Yeah, okay. Yeah, that's a better example. It does matter. Yeah, but you see how if you do
Basically, you do like if you do 1, 2, and then let's do like 1/2 and then 1/. So
it'll
1
be
over
1 over
3
3
and
versus
2.
2 over 3. That's 0.667 versus 0.333, right? But these are higher. So it still does amplify it.
Because when you normalize something, you take the sum of those values, right? And then it's like the ratio of this relative to the sum. So you have two numbers, you pass them to an exponential, it will amplify. If one is bigger than the other, it'll be much bigger than the other. And then normalizing it is just like reducing down this ratio to such that the scale is like 0 to 1.
Yep.
So normalizing doesn't actually affect it. It's just like makes the number smaller, but the ratio is still going to be the same. Genius. Well, you got that already? You got that?
What? Yeah.
Okay, so okay. Like you knew that already, or
Your explanation.
we just reasoned about it.
Yeah.
So it shouldn't matter. When you normalize, you only. Do you like my notes?
Yeah. I was trying to use it for a while, like Obsidian, and I stopped. Got lazy.
You're seeing down the numbers, but the ratio remains the same. And then I think get ready. So this is 1. This is 2. Is that a good way to? No. It's a rectangle. 1, 2. 1, and then normalize. You get 1/3, 1/3, and you get 2/3. And then the distance, like this is 3, right? And then I'll get 1. Okay. And then if we do a exp softmax version, so then this is e to the 1, e to the 2,
And then the total is e to the 3, or e to the 1 plus e to the 2, not e to the 3.
yeah,
Yeah.
plus. And then how does, so the ratio will be, this will be like, right, instead
Yeah.
of being twice the width, it's e to the 2 divided by e to the 2 divided by e to the 1, and it's like 2.7 times longer. 7 only times e to the 1. Alright, and then let's make this. Wow. And this is 1, and then this is e to 1 over, let's just get some. And then e to 2 over s. Right. Right. Okay. You wanna see? I was like doing matrix multiplication stuff and like some pretty cool drawings. For matrix multiplication, I had these.
Oh, nice, yeah.
Like, remember the Siboem log? I guess it's like this. So basically, you have n by k multiplied by k by m matrix is an n by m matrix, right? For each matrix multiplication, it's really just a dot product between the row and the column.
Yep.
So you visualize that, and then I was like explaining, you stored matrix in a row major fashion. So when you index, it goes like this, and when you cache things, and here I was like explaining how it would work when you do the naive matrix multiplication, which is like a row times a column. The first time you have a cache miss, so you would need to read it in, and when you read a cache line, it's 64 bytes. So however many, like if each element is a double, which is a double is 64 bits, which is 8 bytes, then you would read 8 elements. But then your columns, like,
Always missing, yeah.
is always missing, right? And if you have a super big matrix, then after a while your cache is full, so then like these caches will be like removed for those. But I was saying, if your matrix is small enough, then your entire matrix can be cached, in which case like you wouldn't really notice this difference. So whether you do this for really small matrices, it actually doesn't matter. Like, you have a cache miss the first time, but like eventually all of it will be cached. So it doesn't matter. So it only applies for big matrices, this caching mechanism. So it's like this diagram. And then I was trying to visualize, what's harder to visualize is like when you do matrix multiplication and you swap the inner and like that, right? Like
Yeah.
how it actually you're trying to visualize it. It's a bit hard, I felt.
Yeah, I agree.
And then matrix or linear equation system. Or is it matrix? No. 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 Linear algebra? Where did I review my system of linear equation? Oh, like that. Okay, so let's go matrix. So basically, like, you can visualize, right, like a matrix multiplied by a vector is the first matrix multiplied by like a dot product between the first row and the column, and then the second row with the column. So like that's how I, right, because it's like 5 by 4 times 4 by 1 equals 5 by 1. Yeah, just first row times the first column, second row times times first column, etc. But you can also visualize it as this way, where it's a scalar multiplication between the first value and that column. And then once you can see it like that, then you can see that that's why there's if in ax equals b, if x, right, x is your vector and an a, and then b must be created from a linear combination of the columns of a.
Okay, yeah.
And because you can break it down like that, right? The first element multiply the first column vector plus the second element times the second column vector. And so that's why for x to be a solution, like, yeah, there must exist a linear combination of the columns of a to create b. So b must be in the span of the column, or b must be in the column space of a for that to be a solution, right? If it doesn't exist in the column space, then there exists no solution x, right? Yeah, that was from the deep learning book. Like that's how I sort of like.
Yeah.
I totally forgot this stuff.
Yeah, it's been a while since I touched it as well. I know also, like it's used in a bunch of other places as well. Like I guess the most general form would be ax plus bu equals, whatever. If you're doing a control, if you're doing control systems.
Oh. Oh, also guys, Kate Kajanan. What's your his really did I never showed you? Well, I leaked your email.
That's fine.
What's your index right now? Oh, 34. Your O index is 34 right now.
Please edit out my
O
email.
index is basically how often he gets cited in my Obsidian notes. Okay.
Please remove my email though.
It's okay. There's gonna be the professors who are gonna get in touch with you.
Maybe. We'll see.
Okay, so now we're gonna embed a drawing, and then with the solid draw, embed a drawing. Oh. No. Fuck.
Okay, what's wrong?
Embed a drawing, and then arba. No. It was the one I just drew.
That.
Oh, 0202. Computer architecture. Softmax. Yeah. Why is my drawing so shit though?
It's pretty good actually. I'm pretty impressed.
Thanks, KJ.
You're welcome.
I think it's the colors. Like I think the colors make everything good. Like the matrix one is better.
Yeah.
But anyways, I think okay, good enough. Let's not waste more time. Okay, let's get back to the video. So now we understand softmax. It gets rid of negative values and it makes the differences more obvious between these numbers. Is that really needed to make the differences larger?
Yeah, I imagine it's to do with training.
But you have like the exploding gradients problem if like you always make the numbers bigger.
Yeah, but it also helps with training too, right? Because if
You don't want the gradients to explode, so that's why you have batch norm. Remember batch norm?
yeah,
What's the formula for batch norm?
I don't remember. I think if you take a batch and then you sum up. I guess you have it right there.
No, I want you to recall it. I
You-
don't know it at all.
So you have your batch. You take the average of your batch, and I think you divide the gradient update by it, right, or something like that. Okay, never mind. Here it is. It's more complicated. Busy scale shift. So yeah, you do take the batch, like the
Mean the
of
variance?
batch, and then you take the variance, and then you normalize it, I guess, and then you scale and shift it. I guess you have the answer right there. Yeah.
You know? Oh, I need to review the bias of an estimator.
For that, I have to remember second year stats now.
This is really important.
It's been a
Okay,
long
is that
time.
more important than our in understanding transformers? I feel like kind of is sometimes. Bias of. See, the deep learning book has it. Estimator bias and variance. Okay, well this is probably what we do at individual state. Let's watch the. But anyways, it's on my list. Okay, all right, let's go back.
Okay.
But it's an honor to do. Okay,
Mhm.
you don't even know what bias and variance of an estimator is, KJ. How are you gonna?
It's been so long. I have to review my notes.
Yeah, you don't. Clearly, you don't do machine learning anymore, or deep learning.
Dude, I think Loki only do classical robotics nowadays.
And that's kind of sad.
Huh?
Okay, how would you do the inverse kinematics of a 7 degree of freedom robot arm?
Like from, I guess like geometrically. I guess you can't do 7 dots geometrically. But if you could solve it geometrically, I would try to solve it geometrically, but you
You
probably
can't.
can't unless it's a special case.
Well,
Uh,
why not? Why can't you solve it geometrically?
I think there's too many degrees of freedom, right? To the point where it's not possible, if I'm not mistaken. You might be able to, but there's some certain conditions you has to do. Like I think it has to be. I guess I'm stupid. It's possible. Oh, okay, it's just complex.
Do you know the Devin Denave-Hattenberg
Yeah.
parameters?
Basically
Really?
It's huh?
You know the Denave-Hattenberg
Yeah,
parameters?
it's basically just a table, with parameters.
Do I know this? Denav.
You probably do too. It's been a while since I've used it, but it's basically a table.
Mm-hmm.
Like, I mean, the way to solve it is you basically take a table, and then from there you can use that table to compose of, and then from there there's like these matrices, and then, like for example, it's like an alpha, beta, theta, like it's like the length and the angles of it or something like that, and then you basically take that table.
Okay,
and
let's just
then you
start
can
from
compose-
scratch. Let's start from scratch.
Mhm.
Explain it.
Okay, so you have a table.
What the table? What
Like the
dimensional?
manufacturer might define a table
Okay.
of 4 parameters, and these are like angles and lengths of the joint.
So what's x and what's y? So you have 4 columns for the parameters?
Yeah.
And
And
your
you
rows
have-
are the different angles?
No, it's the length of the joint, I think, the angle of the joint, and the other two I don't remember anymore. I don't remember exactly what the parameters are.
Here.
Oh, okay, yeah. Offset from Z to the common normal.
What's the common normal?
So basically...
The base length?
Yeah, so basically if you take the normal of one and the normal of the other, it's the distance of that. So you can think of it as like the distance between the z's almost. And the theta is the angle from the previous z to, from old x to new x. So, it's about the previous z. So basically you have 4 parameters though. It doesn't matter how you get it. Usually the manufacturer will just give it to you.
Oh, this is just the length of the arms then, basically. Or the
Yeah.
length of the links. Right?
Yeah, basically, like, roughly corresponds to that.
Yeah.
And then basically from there you have this matrix. That I don't remember the formula for, but there's a matrix, Yeah, that matrix, I believe. And then from there, what you do is you plug in the parameters, and then you get a matrix. And then what you do is you plug it in for each link, and then if you want to solve forward kinematics, then you could just multiply all.
Where'd you learn this?
Fourth year intro to robotics, and also third year as well, intro to robotics. It's in a manipulation, yeah.
It's in here?
I don't know if it's. Oh yeah, right. It should probably be in forward kinematics in chapter 3.
What is it called? Denavit. See, this is where I learned my stuff from, but
It's not in chapter 4 for sure. It's a classical method. I mean, it's not really classical. It's like still the way people do things.
this was where I learned my transforms, so.
Oh really?
Yeah, spatial algebra right here.
Oh.
See, if they didn't teach me, I'm not supposed to know it.
You can try.
Yeah, why are they not teaching these?
That's kind of surprises me.
What are they teaching? Different. So, they introduce transforms. You can represent Euler angles, and there's quaternions, and quaternions don't suffer from gimbal lock. Oh my god.
Yeah.
But I still don't understand quaternions.
My understanding of quaternions isn't great either, to be honest.
Like quaternions, like for the same orientation, you have two ways to represent it because quaternion like represents the direction, right? Like
Yeah.
one goes like this and the other one goes around.
Mhm.
That doesn't make sense to me though. Like, I don't understand.
I think you can probably just look up like a video.
There's a video, right? Like
Yeah.
Ben Eater and it's like quaternions are online.
Yeah, you should just. Use
Oh no,
this.
that
Oh.
this is another one. Ben Eater quaternion.
Quaternions are a four-dimensional number system, meaning each individual quaternion consists of four real number parts, like what you see on the upper left.
Should have learned this at NVIDIA. I didn't actually. Should have fully understood this. But I didn't really need to understand it, right? It's just like understanding. Like I mostly work in Euler angles because the RDFs don't do.
Yeah, they don't do quaternion.
They just do Euler angles. Yeah, they don't even do rotation matrix whatever.
Yeah, I mean, I think quaternions are more efficient in terms of computation for things, but I always think in terms of rotation angle or rotation matrices, because that's the most intuitive to me.
Yeah, and you know, once you understand that a matrix multiplication by a vector is really just a linear combination of the column vectors, and it's a lot easier to visualize when you're in homogeneous linear systems. You're one, right? Like your last your fourth row of the vector is just a one. So it's one multiplied by the last column, the fourth column, and one multiplied by that column is basically the translation, right? And then the one stays the same, and you can see the other ones, it's zeros at the bottom.
Yeah.
So that's how the one stays a zero. So if you visualize it like that, because if you actually do the multiplication, it's like generally it's like first row times the first column, and then second row times it's like kind of confusing. But if you just visualize it as a scalar multiplication of the columns, then it's like really easy to visualize.
Yeah.
Right. Have you thought about it like that?
Actually, no. The way I think about it usually is more the traditional way of doing it. So the way I think about it is, when you do this one, you get the first one, right? And you're just doing some kind of transformation to get x.
I guess you can visualize as the one is multiplied by, it's like,
because the 1 is 0, 0, 0, 1, right? So, and you know in homogeneous space you have x, y, z.
Oh, that's
1.
if you use the identity rotation matrix.
Uh-huh.
1, 0, 0, 1 if you use the identity.
No, it's 0,
rotation.
0, 0, 1 at the bottom. Always.
Oh, you're saying at the bottom, okay.
Yeah, at the bottom.
Yes.
And then if you have x, y, z, 1.
Yeah.
Then
The
since there's 3 zeros, those mass scale up with the first 3 values.
Yeah.
And you get 1, so 1 is equal to 1, which is true. So that's how I think about that. And then for the other part, it's just like, I just think about it in terms of traditional multiplication.
But yeah, that's how most people think of it.
Yeah.
Useful language for describing and for computing orientation and rotation in three-dimensional space. My goal is for you to come away from this whole experience understanding how exactly that works. And in the spirit of getting you playing with things from the start, I want you to start messing with these four numbers you see in the upper left. If you're on desktop, you can bring your mouse over them and either scroll while the cursor is hovering over it, or grab it to change it. and if you're on mobile, you can tap to interact. And as you change these numbers, you'll notice a couple of things. First of all, changing them causes the sphere that you're looking at to get reoriented.
Whoa.
So this is what we mean when we say
What's
the
this for, though?
quaternion corresponds to an orientation in 3D space. And another thing you'll probably notice right away is that as you change one of these numbers, some of the other ones are forced to change as well. This is because the quaternions which describe rotation in 3D space are the unit quaternions, the ones where the sum of the squares of these four numbers equals 1.
The sum of the
You
numbers?
might also be wondering about the second quaternion written below.
The sum of the numbers is 1?
Yeah, because they normalize it.
But the sum of this is -1.
No, it's you take the magnitude of the vector. So it's negative 0.1 squared plus 0.1 squared plus 0 squared plus 0 squared.
Oh, it's squared.
And you take the square root of that. And so it's the magnitude you preserve.
Hmm.
And if you normalize it by the if you normalize it by the magnitude, then yeah, you get 1. But in this case, because it's a unit vector.
How do you define, you just define it arbitrarily like that? Like the magnitude, like the magnitude of a vector, right? It's like Pythagoras law, so that's why you do x squared plus y squared. Square root of that is your y. But then a quaternion feels kind of arbitrary, the norm, no?
Yeah, it's just a generalization of vectors from that space to a higher space. Like you think about it in 3D as well.
Well, quaternion exists in what? Like quaternion is like rotation matrices have a property as well, right?
I mean, like when you do 3D, why do you take the magnitude?
When you do 3D, why do you? Because it's x, y, z, right? So it's like you get x, y, z, and then like the actual magnitude is that's how you get the formula.
Yeah. So now what happens if you have a 4-dimensional space? You can't visualize it anymore.
Whoa.
Huh?
Yeah, I see what you mean.
Yeah.
But this is not a vector. This is just like some random quaternion.
It's effectively a vector. Like it's a vector with.
I see, because it's 4
properties.
numbers.
Yeah.
Essentially, vector.
So not fully though, because some of the properties
Don't hold. Like
don't
addition.
hold. Yeah, it just has similarities.
Oh, what are it? I have the properties here. In Visual Slam book, that's where I learned my quaternions. Properties: addition, multiplication.
But yeah, you can see multiplication is defined differently than how multiplication is defined in general.
Conjugate, inverse. But how the hell did someone come up with quaternions?
Some really smart dude back in the day. He came up with it.
Why wasn't it you, KJ?
I don't know.
Okay.
I'm sorry to come up with that.
Okay. Quaternions. Okay, well I guess we'll start tracking quaternions now.
Don't worry about that one too much.
We're just like building our foundation up again.
Yeah. What about transformers though?
We'll get to that, but you can't even explain quaternions to me.
Oh, okay.
Can you?
I probably forgot.
Exactly, so you need to refresh it. Like, what if your prof comes up to you and is like, KJ, what's a quaternion?
I'll be like, man, let me review my notes. And I'll come back to you.
When we understand why quaternion multiplication describes.
Every time we learn it again, we get a deeper understanding. Both of you and I don't, like, we know what a quaternion is.
Yeah.
Right? But every time there's new, like, you learn the thing and then you don't absorb everything. So every time you still need something more.
Part of the problem too is if you don't use it, then you forget it.
But quaternions are used.
You don't use it, you lose it, right? So like in my day to day, I don't use quaternions.
You use what?
Rotation matrices.
Oh.
Yeah.
So what are the properties of rotation matrix?
Like they're SO3 matrices. You can multiply them together to come up with a new matrix. You can convert Euler angles into.
What is the properties of SO3 matrices?
It is R transpose R equals identity, I think.
What do you call this kind of matrices?
SO3. Oh, sorry. I know it's like R inverse is equal to R transpose. That's the property. I don't remember the name.
Wait, I don't remember either. Wait, I didn't think. I learned this last week.
But yeah, R transpose is equal to R inverse. And then the other one is that to ensure that it's a right angle. To ensure that's a right coordinate.
How do I not remember that?
Oh. Yeah,
Yeah.
that R equals 1, 2. And that's to ensure that it's a right-handed system. Because if it's -1, then you get left-handed system.
They did teach you here. They teach you here.
Mm.
Types. Oh, maybe it's in my matrix. Types of matrix. Orthogonal. Symmetric. No. Screw symmetric.
Hey, go back to symmetric.
Orthogonal. Oh, it's orthogonal, right?
Yeah, oh, it's an orthogonal matrix.
How am I supposed to freaking remember this?
You don't have to remember it, though. You can just look back at your notes.
No.
Mm-hmm.
It would look like you don't. If you don't even know what it's called.
Mm-hmm.
I guess you knew that it was RT, R equals I. And then there's another one. There's another property.
Yeah, but you pulled it up, so I already saw it. It was
Determinant.
determinant of R equals 1. But why is it equal 1? Why isn't it -1?
The determinant can never be negative, can it? No.
It can be.
Because it's AD minus BC determinant. Is it 1 over AD minus BC? No, that's 1 over determinant times objective.
Yeah.
AD minus BC, yeah.
But there's nothing about it that makes it not be possible to be negative. So why is it that R equals 1? Hmm?
You know why?
Yeah,
Wow,
there actually is
you're
a reason.
Yeah, I'm sure there's because RRT equals I.
No, that's not the reason. The other property isn't if R transpose equals I is sufficient, then they wouldn't define the other one.
Yeah, but basically, like, when you multiply two SL3 matrices, they stay in SL3, right?
Mhm, yeah.
So, if the determinant was 1, maybe, like, that could cause it to not be,
Mhm.
part of, like...
I'll give you a hint.
It's like a linear...
What coordinate system do we usually use?
What coordinate system?
Yeah.
What do you mean, what coordinate system do we use? Like, R3?
Like, suppose I'm doing the cross product, for example.
Are homogeneous?
No. How to determine what, like, there's two different types of coordinate systems I could use. I have two hands,
Okay.
a right hand and left hand.
Yeah.
Which hand do I use? Which hand I use?
The right hand rule? Or is
Yeah,
that,
exactly.
how does it have to do with...
It's a right-handed coordinate system.
So that's why it's a 1 and not...
Yeah, that's why it's not -1. Hmm?
Okay, I'll see if you're right.
I hope I'm right. Otherwise, that means I forgot, and it could be a different reason.
That is-
Yeah.
I don't understand though.
Hmm? So, there are multiple types of transformations, right?
No.
S-
Sure.
Oh, yeah, exactly. Nice. That's the
Nice.
table. Nice. Yeah. And so with this table, you basically want to preserve length, angle,
and volume.
Yeah, but if the determinant's non-negative, then if the determinant's like not 1.
No, but what if it's -1?
Hmm?
I think if it's -1, you still preserve the length, the angle, and the volume, no?
Hmm?
Can it not preserve that? The length, angle, and volume?
Yeah, I think it preserves that, but it might reflect instead and stuff. Yeah.
And that's bad.
Yeah.
What if it's...
I mean, if you think about it, if you have, like, if I have my object like this, for example.
And then it becomes like this?
Yeah, I can't like, I guess I don't have to show reflection.
It mirrors. Imagine the text is just mirrored.
Yeah, you can't do that. That's like cheating. That's like not what the real world does when you rotate something, right?
Yeah.
But if I have this and I move it like this, the text is still the same way, but just I moved it in space and rotated it.
What's an affine transformation?
Affine. Oh, I guess you have the solution.
I don't have it.
Huh?
What are the properties?
Oh, oh yeah, that makes sense. Affine with the offset. Kind of cheated. That's actually why y equals mx plus b, for example. is an affine transform because there's an offset. It's not actually a linear transformation.
You okay?
Huh? Yeah.
I during my second internship I used affine transformation.
Oh. I don't think I've ever used them. I might be lying, but I can't think of a case where I've used it. Yeah.
I still haven't internalized this. So an RT is a orthogonal matrix, right? So when we say orthogonal, orthogonal vectors are vectors where their dot product is 0 because they're exactly 90 degrees to each other. And dot product is defined as could be defined as element wise multiplication summed, or you can is the norm of A times norm of B times the cosine of their angle. And since the cosine of 90 is 0, then the dot product is 0. When we refer to orthogonal matrices, I think if you look at the vectors themselves, they're actually orthogonal. Is that true?
Yeah, they should be true. Like if you multiply,
you know what an orthonormal matrix is?
It's the same thing as orthogonal, isn't it?
Orthonormal vector versus orthogonal.
I thought they were
Vector.
the same thing.
No.
What's orthonormal defined as again?
It's orthogonal plus normalized.
Oh. Yeah, you're right. Good job. Wow.
Yeah, so I don't think you say it's an orthonormal. You can't just say like one vector is orthogonal, right? It's like it's orthogonal relative to another vector, right?
Yeah.
So yes, generally you say like orthogonal basis, and then.
But like a rotation, like you can think of another way of thinking of a matrix is a set of vectors, right? Because you can compose a matrix. Like a matrix is basically just like four like a rotation. Yeah. Because basically, like the columns of a rotation matrix are just vectors.
Yeah.
So you basically have three vectors.
And each vector is their length is 1, right?
Yeah.
Is what I remember.
Mhm.
But then SO3 doesn't have that definition, or is it like by the fact that they're orthogonal matrix, it's an orthogonal matrix, right?
Yeah, I think it's baked into the fact
because a rotation. Because I remember when I just remember the vector columns are like length 1 are normalized, but I didn't remember the definition of SO3, like it's actually called an orthogonal matrix.
I didn't remember that either though. I remember SO3.
Yeah, so SO3 it's an orthogonal matrix, which means that RRT equals the identity matrix, or you could say R transpose equals R minus 1, right? Because RRT multiplied by R minus 1 on the left, and you get R minus 1 on the right. But the determinant, that part, I'm still a little confused. Why it's equal to 1. Like, what happens if it was 0.9 again? Like, why isn't orthogonal enough?
I think it has to do. So if you think about how you compute the determinant.
You want to stand up? Let's stand up.
Oh no. Dude, I never understood the idea for why people like standing desks. I guess I understand it. It's like supposed to like simulate like standing.
What's happening?
I think it's at its limit.
Oh.
Mike's set broken too.
Mike's might have broken. Okay. Why is the lighting so bad? Yes. Yeah, we were saying?
Yeah, so I think it has to do with the fact that one of the properties of determinant is when the determinant's 1, then your matrices are, what's it called? They're orthogonal, right? Or an inverse exists is 1. The determinant's, what are the properties of determinants? Oh my god, I can't believe I forgot this too. You know how the proper. There's like a bunch of, like, if the determinant's 1, then an inverse exists. Yeah, that's good to ask.
Okay, yeah, you said special.
Mm.
Preserve volume and orientation, I guess.
Mhm.
Doesn't the fact that doesn't a matrix and orthogonal matrix preserve volume and orientation?
Yeah.
You don't know?
Does not always preserve orientation.
Rotation matrix. Which preserves and used to preserve volume. However, it doesn't guarantee preservation of orientation. That are because on guarantees that orientation is preserved. But so why do we need to have the matrix be orthogonal in SO3 if E equals 1 already into volume and orientation? I asked some good questions, huh?
Yeah.
Let's see. I guess the volume could be the same and the orientation could be the same, but like it could be a different shape. Like
Yeah, like I guess like a shear matrix would like if you have like this, for example, and it stretches it out, that's like not good. Or you have like a square and then you stretch it out, it's not good either.
both. Stretching, but volume condition. So what's the isn't this cool? Like this is not more. You're just learning. Isn't learning so fun?
Yeah.
Okay. I hope you're learning too.
I am.
Okay.
It's good review. Like I said, I forgot everything.
But reviewing is useless.
Really?
Yeah.
Why?
Because you'll forget it. If you don't use it, you'll forget it.
Yeah, I agree.
So just
I said that before. I always said that.
But I'm not reviewing. I'm just learning.
Yeah.
I guess I'm not learning. I'm reviewing.
Yeah, you're reviewing.
No, but I actually didn't know this stuff before.
But aren't you asking for your interview?
Okay. Yeah, okay. Me, it's because I'm interview prepping.
Wow.
And also, it's fundamental knowledge.
Yeah. Well,
If you go to up someone and they don't know linear algebra, you're like, this kid doesn't know what he's talking about.
I think
What do you think?
If they can review it and understand it, it's fine. I'm not like too big on like it's important to know it, but if you forget, if you know the basics, it's important. But if you get specific properties, I usually don't think it's a big deal.
Oh, but if someone like ask them to understand quaternions, I feel like some concepts, if they just like cannot,
Yeah,
there's some things like you just like cannot explain, like what's a static variable.
Well, static variable is actually kind of complicated as a concept because depending on the language, it's like different, right? Even in C++, like if you do it like static, like
what's a translation unit? You know what a translation unit?
Like in the MMU, or in the
MMU.
Sorry, I'm thinking of emulators. Isn't it compiler?
Yeah, compile.
I think it. I mean, I guess it takes the code in assembly and translates it into binary. Or no, it takes the. I don't know, dude. I don't know how compilers work.
It's like the smallest unit of compilation, so it's essentially like a source file plus all the headers that it needs, and you compile that down to like an object file, and that's like a translation unit. Yeah. So you have a bunch of translation unit, and after each of them are compiled, you'll link them together. So like static variables only exist within the same translation unit, or they're only visible within the same translation unit. Yeah. So each translation unit, the static variables will, like you won't be able to use that. And then you have extern, which just means it will come from somewhere else, not defined in the file.
Wow. I feel like we talked about that last year.
We did?
Yeah.
Yeah, and I was like this week I was reviewing this stuff and it was kind of cool.
Oh, yeah.
Why the second one has
Are we done with the SO3? So you want to maintain the relative sizing of the vectors as well, like not just the entire matrix, but also within the length of the vectors and angles between them within the same vector. You want to preserve the properties. That's why you need it to be an orthogonal matrix. Like matrix, so
I guess it basically gives you guarantees that particular properties of the object, specifically the orientation.
So orthogonal matrix, the columns and the rows are all like normalized, right? They all have length of 1. And they're all orthogonal with respect to each other. So is that true? Rows are mutually orthonormal, and columns are mutually orthonormal. So they're orthogonal and they're normalized. Yeah, that's a really cool matrix. Yeah. Did you know like the rows are also their length is sum to 1, not just the columns?
I guess so. Okay. I don't think I knew that.
Okay, we don't need to know that.
Yeah.
Okay, so you only need rotation matrices. Okay, but quaternions are superior. Yeah. Because instead of 9 numbers, you only need 4 numbers. Yeah.
Well, what you could do is convert your rotation matrix to a quaternion and then use a library to count the math for you, and then you're good.
How do you convert a rotation matrix to a quaternion?
You use a library.
Okay.
I think there's a... Wait. No.
I'm tired. That's it. Do you need a drink?
Yeah, I'll take a drink too.
Which drink you want?
I'll come back. I might take a fancy drink. Huh? I might take a fancy drink.
going down. We're long timber. I gonna move.
Module, my only goal is for you to build an intuition for which quaternion corresponds with which rotation. And depending on how brave you are to poke around and see some of what else is lurking within this applet, you might get to a point where things start looking truly strange. And that's because in some sense, the image I have initially pulled up here of what seems to be this dimensional sphere in 3D space is actually part of a much broader concept of a four-dimensional hypersphere.
Whoa.
Later modules we're going to come to understand. But for the moment, for the purposes of just building up the intuition on which quaternions give which rotation, you don't need to worry about that. You can just think of this as an ordinary sphere in ordinary 3D space, no added frills or complications. One of the first things you might do to build a little intuition is notice how this sphere changes when you just change the I component to go from 0 up to 1, or if you do the same changing the J component to go from 0 up to 1, and likewise for the K. And if you want, please, by all means, pause my voice and just keep playing with that if you feel like there's good intuition to be built. But a slightly more generalizable way to understand which quaternions give which rotations will involve changing the representation here to a certain angle axis representation. So in this case, the real part is written as the cosine of a certain angle. And you can think of the three imaginary dimensions as representing a certain axis
Oh,
in
right.
three-dimensional
It's actually 3 imaginary with 1 real number, right? Not the other way around.
Yeah. That's why it's IJK.
And W or something?
Oh, yeah.
IJ. Oh, and then just nothing. I guess Q0 IJK. Axis angle representation. An axis angle representation is just like a vector with a magnitude, and the magnitude represents the rotation around that vector.
No, so it's... Yeah, kind of like that. So
It's just on
you have a vector, not a magnitude, just the vector itself, and then you have the angle.
the angle is represented by a magnitude.
Yeah.
But how do you get it? Like, you have a vector. Let's say it's 1 0 0, and then what?
And then...
Or it's
angle.
x.
Yeah. Then you
Okay.
have your angle.
And go like that. Like,
Yeah.
How do you know it's like that or like that or like that?
1 0 0, because 1 0 0 points out this way.
Mm-hmm.
So
So then,
the angle's about that plane, right? Right here. Let's just.
oh, that's how you do it.
I think so. Yeah.
But how do you know it's like that or like that?
Axis. If you look at a picture, it'll be useful. So you see how in this case, this is pointing this way, and then the angle is defined as the plane. Like it's
Yeah,
like,
of course. But where's the 0 angle? How do you know the 0? Where's the 0?
The 0 would be
0 degree. How do you know?
That's actually. I guess this.
Ah, you never thought about this.
Never thought about that. Yeah.
See, that's where people think they understand, but they don't actually understand.
Yeah. Because with this representation.
Yo, you know who this guy is?
Who's he?
Oh, don't show his name. His name is. Oh, he's the guy behind Oculus.
Oh.
Stephen Lavelle is the
damn.
planning algorithms.
Yeah, I remember that book. I never read it though, but a guy mentioned it in class.
This is really good, right?
Yeah, I'm actually pretty surprised. It's really good.
Yeah, you're welcome. This one's pretty bad.
You want me the higher quality $1 one?
This is actually more expensive, I think.
Oh. He has a VR series.
Mm-hmm.
Interesting.
I mean, the picture was actually not bad.
You can ask ChatGPT, what's the 0 angle? I've outsourced my brain to ChatGPT.
I'm also your brain to change.
I think all we're showing is the generation's cooked.
Huh? All the way?
I think all we're showing is our generation's cooked.
Yeah. like everything, all this knowledge that we tried to accumulate for the past 20 something years of our
Yeah.
life, is just like ChatGPT knows it all.
Yeah, I know.
Yeah, we're cooked. I mean, ChatGPT's IQ is like 120, 130.
Mm.
So you like if ChatGPT can't create new knowledge, you think we can?
Yeah, maybe one day.
One day ChatGPT will create knowledge.
Mm-hmm.
Well, that very soon. Probably Wikipedia has it. Isn't it? I guess it's representing a rotation, so it's like relative to your current coordinate system.
Yeah.
Right. Rodriguez rotation. Oh wow.
This is the conversion between.
Yeah. It's always your current. Okay, so that's it. Yeah, like it's x equals 1,
Mhm.
and then you rotate. So you imagine a circle around it,
Mhm.
and then if it's like 90 degrees, then you rotate 90 degrees,
Mm.
like that, right? And then if it was like here, it's like rotation
Yeah.
90 degrees. Cross product. What's a cross product?
It's I mean, you don't remember this, right? It's
I don't remember this.
Okay.
You remember this? See, if
Yeah.
you ask someone and he's like, "What's the cross product?" and they don't remember, it's like if you ask someone what's the dot product and they don't know the dot product, then they really don't know what they're doing.
Cross product is basically you take two.
But would you say cross product if they don't know? They're also stupid.
No.
No.
I mean, if they didn't learn it, but if they forgot it, it's fine.
But like some things, like if you forget what a dot product is, then it's like actually.
I mean, it happens too. Dot product is the easier one to remember, though. It's also the more like.
But if you don't remember that, that means like you never use it.
Yeah, but like cross product is just a determinant.
It's the area of a parallelogram. That's what I remember.
Yeah. So if you take ijk as the top of your cross product, and then you have the two vectors written out, then it's basically just the determinant formula.
Wow, we look good.
Oh yeah.
Okay, wait, you were saying? Cross
Oh, yeah.
product. Yeah.
Cross product is basically just a determinant, and so. Oh, you're pulling up.
No, but you explain it. I'm
Yeah.
just like fact checking you right now.
Okay. So basically, if you have two vectors, so let's say you have like one vector going this way and another vector going this way, and you want to find out the other vector that's normal to both those vectors, then you can do the cross product
Oh, right.
to determine
Yes.
the other normal. So it's basically to get the third normal. Yeah. You even have the definition. Oh my god.
I have the area, but this is called the area. This is the norm of the cross product is the norm of
No,
Okay.
this is the magnitude.
magnitude is the norm. No.
Oh yeah, it is. Wait. No, norm is when you normalize it too, right? If you wait.
What? Oh, that's something else. Norm. Oh.
Oh yeah, you're right. It is the same. Vector norm and magnitude are the same thing. Good job.
What, you were gonna say it's like the normalized version of a vector?
Yeah.
No, KJ.
So stupid.
Vector.
In this
No,
video,
we
we're
don't-
talking about the kinds of vector norms. And what I
We
mean
don't
by
have to
vector
watch this
norms
video.
is kind of different ways to measure the magnitude of vectors.
We don't have to watch
And now
this
you're probably
video.
thinking, well, I already know how to measure the magnitude of a vector. But the way you know it is probably the L2 norm, which is the way that's most commonly taught and used very frequently.
See, I say norm now because L2.
L1 norm, L2 norm. Yeah.
That's not even correct. Wait. It's called the matrix norm. Matrix norm.
Vector norm.
Vector norm. L2 norm.
Yeah.
Matrix norm. Matrices can have norm. You can quantify the magnitude of a matrix.
Yeah, I think I learned about that in control theory.
It's called the Frobenius norm.
Okay, I didn't learn that. But we did learn about matrix norms in control theory, or linear control theory specifically.
You want to do some? I was gonna say CP, competitive programming.
No.
Okay. Alright, we got sidetracked.
Mhm.
This is good to know. Like we're just like
Yeah.
we're like doing like reviewing all the fundamental robotics concepts.
Scale
Yeah.
down by the sine of that angle to make sure that the whole thing is still.
Because he talked about
Mhm.
axis
So
angle
it's still just
representation.
four numbers where the sum of the squares of these numbers is constrained to be 1, but it's written in a different notation. So right now I have that axis set to be fully in the I direction, which you can see with this pink vector coming out of the middle. And what I want you to do is play with this
Why'd you go away?
value for the
Nice.
angle. Notice what it does to the sphere and see if you can predict which angles correspond to which orientations.
Yeah, axis angle representation. 0 is like this, and then you rotate.
So the
And it's
first thing
right-hand
you'll
rule,
notice
so
in
you-
doing this is that everything is rotating about the x-axis, which corresponds to the number I. Now, another thing you might have noticed is that there's a certain angle doubling thing that happens here. Notice, when we change this angle from 0 up to 45 degrees, the sphere is actually rotated 90 degrees. And if I push that up to 90 degrees, the
Oh,
sphere is actually rotated 180 degrees.
Really? Is that what we
That's
observed?
the theme of this. And what I want you to do is play with this value for the angle. Notice what it does
Yeah.
to the sphere and see
But
if
we
you can
rotated
predict
90 degrees.
which angles correspond to which orientations.
Is this a 90-degree rotation? Why is it only 45?
So the first thing you'll probably notice in doing this is that everything is rotating about the
So
x-axis,
cos
which
45
corresponds to the
is
number I.
Root 2 over 2.
root 2 over 2. And then sine 45 is
Root 2 over 2.
root 2 over 2. And then what's 1i plus, so that's 1i plus 0j plus 0k.
Uh-huh.
So the other two components don't matter. So what's root 2 over 2
Pa-
I equal to? So it's so then you end up getting a quaternion. It's basically root 2 over 2 I
Plus root 2 over 2.
it's like root 2 over 2 I comma 0 comma 0 comma root 2 over 2. And so in quaternion space, I guess this is the 90-degree rotation, right?
Mm-hmm.
So that's why. Because there's the two components, right? Like the real part shifts the entire. Oh my god, I can't be on your phone now.
Sorry, Sasha.
It's okay.
Sorry, Sasha.
It's okay. I don't know what I'm talking about anyways.
No, it's because I have a dinner at
Hmm?
the Chinese New Year parade.
Oh. Wow, I wasn't invited.
Can you read this?
Go back to this. I can read that. Oh wait, never mind. I can read this though.
What does it say?
2025 SF Chinese New Year parade. What does that mean?
There's a parade
Mm-hmm.
in 2 weeks from now.
Oh, in 2 weeks? I thought Chinese New Year was like now.
Yeah, we celebrated.
Hmm?
We celebrated already.
Oh, wasn't it?
But they have like, I don't know, it just keeps going.
The party never stops.
Yeah. Oh, it's like for 2 weeks. Alright.
Okay.
So root 2 over 2 and root 2 over 2, and then what? So how does that relate to like 90-degree root?
Because I guess if you look, can I go back?
Oh, you split it into two components, and like so it's 45.
Yeah, like
and
the real
45, and it's
real
90.
component is root 2 over 2, and then x, like the I component's root 2 over 2 as well. Can I go back a bit?
Yeah.
So if you look here, for example, if I put this to 0, or sorry, no, if I put this to
Root 2 over 2?
yeah, like roughly there, I think is good enough. And then if I put this to
The other change is at the same.
yeah, this is
Because the norm is the same.
yeah.
The norm is 1.
But you see how when you shift this, you shift like, I guess kind of like the sphere. So if you look at this, this is now like the rotation, right?
Mm-hmm.
Because these two components shifted. So that's basically why it's 90.
Hmm.
Yeah. But he probably will give you a better explanation than me.
So up to 45 degrees, the sphere is actually rotated 90 degrees. And if I push that up to 90 degrees, the sphere has actually rotated 180 degrees. That fact might seem a little bizarre, but it has to
That's
do
also a good idea too, because cos 90 is what?
1.
1. Sine 90 is what?
Oh, wait. Cos 90 is 0.
My bad. Yeah, cos 90 is 0. What's sine 90? 1. So then you end up with wait, no, sine 90 is yeah, it's 1.
Yeah.
So then you end up with 1i plus 0j plus 0k
Plus 0.
plus 0. And so 1i corresponds to the 90 degree rotation, right? Because you rotated only in the I component.
do with the idea that there's two quaternion products happening here. One by q from the left, and one by q inverse from the right. Where in the angle axis representation...
Why does this look like the singular value
just by
decomposition?
negating that angle.
Or this is the eigen decomposition.
Eigen decomposition, what's that?
It's when you split into eigen. You write the matrix as a product of the like an eigenvector matrix, and then eigenvalues diagonal matrix multiplied by the inverse of the
right. I remember that now.
of the. Wow, you know that?
Yeah, it's a similarity transform.
What? What the fuck is that?
I think it's called similarity transform, right?
Similarity is what we. How is that different from an affine transform?
Wait, go on Google. Look up. I thought it's called similarity transform. Yeah, a similarity transform.
Whoa.
Mm-hmm.
Eigenvalues.
Yeah.
Whoa.
They are the same as eigenvalue, eigen decomposition.
Is it the same?
Yeah, it's the same. Oh. No, but they're basically this. They're basically this. Dude, they're basically
Wait, why is this the inverse first?
Oh, wait, other way around.
Wait, what? You shouldn't trust ChatGPT all the time, though.
Yeah. Dude, this is why you can't outsource your brain yet. We're close.
And we need O3. O3 mini high. Reason about it.
Oh, he's explaining what he's thinking about? Wow. This dude's smarter than me.
Wait, similarity transformation. Is it the inverse actually first? But in the image, it's actually not.
Oh no. Back to geometry.
I think it got trained on this, and this uses inverse.
Yeah.
Is this what you mean by? But what's this?
It's basically you take something, you transform it to some space, and then you untransform or something along those lines.
Oh, equivalent.
I think I was taught that it's an example of one.
Singular value. That we know.
SVD.
The particle accelerator.
Yeah.
What do you call this formula?
the eigen problem. I don't know. It's like the determinant of, like, I know what it does. I was like, this helps the eigen problem. The characteristic equation.
Yes, good job. I'm
Oh.
so proud of you.
God.
Is that what it is though?
Yeah, I think it's called this.
Isn't it SI, like?
SI? What's SI? Maybe. Wait. Oh, you might be right. Oh shoot, I'm stupid. Wait, am I right? Oh yeah. Oh, whatever. Close enough. Characteristic polynomial. Close enough.
Oh, it is that. It is
Yeah.
that determinant of A minus.
Yeah.
Well, S. Yeah, where S is the eigenvector, eigenvalue, and then.
Yeah.
Dude, what is the freaking similarity transformation?
It's like. Right. It's like right.
I had it, but I don't have this freaking formula. What's this formula about? Like. Dude, I don't want mini high, bro. Maybe we should use DeepSeek.
Yeah. That's. Oh wait, go down and jump in your algebra. Yeah.
So you did you learn as that or as PAP minus 1?
I don't remember which one I learned anymore. It's been a long time. It is actually a useful concept to know. I remember I was like doing some math and then for some reason it like showed up randomly. I was like, cool, and then I used it.
You were doing some math and it showed up randomly.
Cause I was doing something to do with, I guess, like coordinate transforms for motion compensation at work. And then
Don't leak IP here.
oh okay, yeah, I was doing something secret. And it showed up randomly. I was like, cool.
Well, you can explain what motion compensation is to the audience.
Okay, so basically, when your thing is moving really fast, and you want to compensate for motion, and you have like an odometry source that you consider more accurate.
What's odometry?
Basically, like if you know your position and orientation of the robot well, and then as you're driving, you have like say a lidar. But then the problem is, as you're driving, the lidar beam, like if you're going really fast.
What is odometry?
Huh? I'd say it's basically just the position and orientation of the robot. What? Like relative to some fixed frame.
Odometry is a measurement of how fast you're moving, or like it's a source of.
No, it's
your odometry tells you how much you've moved.
Yeah, so it's the position and orientation of your robot relative to a fixed frame, basically. But yeah, so basically, odometry tells you like it's an estimate for where you are, and then basically, at least with motion compensation, if you have a lidar, for example, and if you're going really fast, what ends up happening, like if you think about lidar beam as like a scanner that kind of goes like 360, if you're going really fast, that scanner gets kind of distorted, right? Almost like a Doppler effect. What? Yeah, almost like the Doppler effect, where it's like the beam gets kind of distorted, and so you want to correct for that. And so if you have,
how does it get distorted?
Because you're moving. Your robot's moving faster than this lidar can scan the environment.
Yep.
And so because of that, you want to compensate for that and like correct the beam so that there's no distortion due to motion. And so one way you could do that is if your odometry has a high enough sampling rate, then you could basically just use that and use the difference between two positions and then do a bunch of math, and then you can compensate for that.
But
motion.
what if you're using your lidar to do SLAM? You don't even have an accurate source of odometry because you use your SLAM solution itself as the source of odometry.
Yeah, so in our case, we weren't using. Our case, I can't. It's IP, but I can't.
You have encoders in the wheels.
No, we didn't. We had visual SLAM. We had cameras as well.
But like, you need to compensate for you need to motion compensate your lidars to run the SLAM properly.
No, we weren't using the lidar for SLAM at all.
Oh right, you had a camera based solution.
Yeah.
But in cameras, you also have, if you have a rolling shutter, You need to compensate for it as well.
Yeah. I didn't know the details of the visual SLAM algorithm. I only knew the details of... Like, I only focused on what I needed to focus on, which is just compensating for motion.
I see.
In the
But we love slam.
Yeah, we love SLAM.
No, slam is useless now.
Oh.
Slam is dead.
Yeah.
Oh god, I don't even know what we just learned here. What's the thing you said?
Definite Horton parameters. There's actually a very good... You go on YouTube. There's a really good visualization of it. That's how I learned to understand.
Dude, you're a robotics expert, sir.
Me? Not really. Yeah, this video. This video is very useful for understanding it.
So Herrenberg parameters allow you to succinctly describe the motion of a series of rigid joints. This is useful for efficient calculation of forward and inverse kinematics. The process begins by defining the z-axis, along the axis of rotation for revolute joints, or the axis of translation for prismatic joints. Since this is the first joint, the x-axis...
It might have not been this video, actually. I don't remember.
Joints, each x-axis will point away from the previous joint.
Yeah, cite me, that's right. Increase my own.
Now, if we add another joint, we can determine the transformation between them. As before, the z-axis points along the axis of rotation. The dh parameters will be derived from the common normal between these z-axes.
Is it this video?
I think it might have been. No, it wasn't that video.
Hey guys, and welcome back to my channel.
Yo, she's messed up.
Oh, nice. You can reach out to her.
We have that.
Oh, what is she? Did she have a startup? PhD.
Oh. Oh no.
Hi friends, and welcome to this YouTube video. In this video, I will be talking about the pro and cons.
Oh, I'm not
of
recording the
PhD
audio.
And the reason why I chose to do one. So obviously, this will be, from my experience.
She did a PhD.
I'm doing a PhD at the Technical University of Munich.
Oh, Munich.
Oh,
Germany is
Tom.
around, 3.5
Tom Robotics.
Tom, yeah.
If I
Yo, she's a roboticist.
Yeah, if I get cooked by...
I started to apply for jobs during my master's, and these were basically the descriptions of the jobs I applied for. I always tell people to still apply, even though you don't hit the mark.
Yeah, if I get cooked by the American schools, I'm gonna look to Europe, maybe.
Oh, I'm gonna put
Huh?
Kicks.
We have eggs here. Oh, that works okay. This is our white syrup. Okay, so now it's a little bit more interesting.
I'm curious what she's doing now. What do you think? Did she leave robotics behind? Quant research.
Oh, at NASA though. At NASA. What does that mean?
How do you?
So what does she do now?
Yeah, I'm very curious. Yeah, she stopped coding. She stopped coding. ICP. How to become I guess she's a data scientist. Okay.
Sorry, man. I stopped coding too. I don't code anymore. I'm like high level thinker. You go on my GitHub, it's dead as well.
Angle doubling happens. For example, how
No, okay, I don't want to expose you.
Yeah, don't expose me.
Rotation.
You already exposed me enough. My email leaked.
By Q corresponds to rotating by 45 degrees, but altering that sphere in a certain way. Multiplying by Q inverse from the right, where with quaternion multiplication, it matters which side you're coming from. Involves continuing that rotation, but putting the sphere back in place. Don't worry if that doesn't make sense. I just want to give a little hint about what's going on. So the next thing I want you to do...
What did he say?
I didn't pay attention.
80 degrees. That fact might seem a little bizarre, but it has to do with the idea that there's two quaternion products happening here. One by Q from the left, and one by Q inverse from the right. Where in the angle axis representation, you can think of Q inverse just by negating that angle. Just to give a little sneak peek as to why this angle doubling happens, for example, how putting 45 degrees in here gives us a 90-degree rotation. Multiplication by Q corresponds to rotating by 45 degrees, but altering that sphere in a certain way. Multiplying by Q inverse from the right, where with quaternion multiplication, it matters which side you're coming from.
So he's explaining it as because f of p, when he plots the f, it's actually qp times the inverse of q. And so when we did 45 degrees, it was actually multiplying by 45 and then applying another 45-degree rotation.
Yeah.
Cause and then you visualize it like this way. He sets this to be like the zero quaternion.
Rotating by 45 degrees, but altering that sphere in a certain way.
Yeah, I think I'm a fraud.
Multiplying by Q inverse from the right, where with quaternion multiplication, it matters which side you're coming from. Involves continuing that rotation, but putting the sphere back in place. Don't worry if that doesn't make sense. I just want to
I have no stamina now.
what's going on.
I used to be able to grind for 10
The next
hours.
thing I want you to
Really?
do is
I'm tired
change
now.
this
Me too.
axis by
I had such
altering
bad
the
sleep
values
last
of either
night.
I, J, or K. And as you change one of those values, you'll notice that the other ones change. And the reason for that is to constrain it to always be a unit vector. It has to be the case that the sum of the squares of these three numbers equals 1. So you're
You're not
playing a sort
listening.
of
I can
continuous
tell.
whack-a-mole. So
I'm
go
trying
ahead,
to, I'm
change
trying
that
to, I'm
axis
trying
in some way, and then notice how the sphere rotates when you then change the angle.
What? I
But
didn't know.
putting the sphere back in place. Don't worry if that doesn't make sense. I just want to give a little hint about what's going on. So the next thing I want you to do is change this axis by altering the values of either I, J, or K. And as you change one of those values, you'll notice that the other ones change. And the reason for that is to constrain it to always be a unit vector. It has to be the case
Well,
that
he's
the
just
sum
called
of
it a
the
vector.
squares of these three numbers equals 1. So you're playing a sort of continuous whack-a-mole. So go ahead, change that axis in some way, and then notice how the sphere rotates when you then change the angle.
It rotates around the axis. No shit.
What
Try it
you'll
again.
notice, and maybe this is what you'd expect, is that the values for I, J, and K determine the axis of rotation. As before, you have an angle.
Well, that's because you wrote it in axis angle representation, bro. But that's how it works.
80 degrees rotates the sphere a full 360 degrees.
I guess it's surprising that mathematically works, I guess. But, right?
It's like a lot more elegant than you think, right?
Right? It's like, oh, of course it works that way, but like mathematically it just works.
Yeah.
It's kind of interesting.
Yeah. Yeah, how could you like roast him? He's like the savior. He's low-key, this man taught me linear algebra.
Loki, yeah?
Yeah, in first year. I grinded his videos. And actually there's an Waterloo open math thing I grinded as well. That's how I learned linear algebra.
Dude, why is there so many... A double cover... Okay, well, I understand double covers, because that's like... You said you also don't understand how it can... Okay, so you never watched these videos?
No, I actually never have. I probably should.
Okay, let's watch it.
Yeah.
Are you down or like you want to do it?
I see transformers.
Over many different.
Yeah, we'll do one more. The
One
2
more.
minute, the 2 minute one, okay? And we'll do Transformers. But you don't even need to use Transformers at work as well. So.
Dude, I use nothing at work.
So just to give you a little more concrete challenge, I want you to find for me which quaternion corresponds to a 270-degree turn around the z-axis. Okay, so 3/4 of a turn around the z-axis. Let's say in the counterclockwise direction as you face it from above.
So it'd be 270 divided by 2, so 135. So cos of 135, right? And then, but first you need to rotate it. So it'd be I, j, k. So you need k to be 1, right? And then 0, 0, 1, and then 135.
Try it.
135. And then 0, 0, 1. Is that correct? Around the z-axis, right? Is that what we did? Yeah. So it was like this. So we flip it to the z-axis, and then we do 135. Oh my god. Okay, you do the next one.
Alright, so the way you do this is first set the axis to be fully in the z direction. So the k value is 1, but the I and j values are 0. And as we alter our angle here, bringing it up to 45 degrees gives us a quarter turn. Changing the angle up to 90 degrees gives us a half turn. So it's when you change it all the way up to 135 degrees that we have 3/4 of a turn. So rotating the sphere 270
I'm confused.
degrees
This is not how quaternion is
changing
actually.
this angle to be half that, 135.
Like, why is he multiplying an inverse? Like, of quaternion? Like, isn't it just QP? Like,
Yeah, I don't know either why there's the inverse in these explanations.
And if we change out of the angle axis representation, we can see this simply as a quaternion with 4 components. And you'll notice that it has equal parts real and k. But I want you to notice one more thing here. There's two ways we could think about orienting the sphere like this. What I just did, we rotated it 3/4 of a turn counterclockwise, right? But you could also just rotate it negative 90 degrees, which involved changing that angle to negative 45. And when you do that, and you look at what quaternion's being represented, again, it's equal parts real and k, but it's actually the negative of what we had before. Before, the real part was negative, and the k part was positive, but here the real part is positive and the k part is negative. So we have two separate quaternions corresponding to the same orientation in 3D space. The phrase you'll sometimes hear referring to this phenomenon is that quaternions are a double cover for rotations in 3D space, which basically means any given orientation corresponds to two separate points on the opposite side of a hypersphere in 4 dimensions that we...
A hypersphere.
It's like a sphere that you can't really represent.
What's the equation for a hypersphere?
I don't know. But yeah, it's like a sphere that's in another dimension. It's like 4-dimensional, right? We can't really visualize quaternions well because it's a 4-dimensional concept.
I mean, we can imagine a hyperplane.
Really? How?
If it's three-dimensional, it's like two vectors. If it's two 2D vectors or two 3D vectors, if it's 4-dimensional, it's three 4D vectors.
Yeah, I know. I mean, it's a similar idea that you can like.
Yeah, 1 dimension less.
Yeah, but it's similar thing with hypersphere. You can't really like, visualize it, but you can like think about it a bit, I guess. It's like.
Yeah, I can visualize it. We visualize the 4th dimension as time, right?
Mm-hmm.
Like when 3D, and then you can imagine like a bunch of cubes like moving across time, but you'll just have one cube, so you can only move alongside one time dimension. And then a 5th dimension is like time, and then there's another 5th dimension.
What's the other 5th dimension?
I think that's how you visualize it. I think there's a video like how to visualize. Also, I should put a timer for it in 15 minutes because I'll drive you back.
Is there also a game like 4-dimensional chess or something like that?
Oh yeah, you want to play chess?
In this video,
Only 4-dimensional chess.
to visualize 4 dimensions.
I'll have it.
Oh no. Really?
Yeah.
You go first.
One try?
One, sure. I need like.
No. Yeah, I'm very slow right now.
Yeah, I'm probably be slower. You're so good. How did I restart it? Tab, right?
Yeah.
Also, this is my first time using this keyboard.
But it's a very nice keyboard.
Is it start? No, right?
No.
Okay, wait. Let me just like.
He's nervous.
Yeah, I'm nervous.
Oh, is he gonna beat me?
Shoot.
He beat me. Alright, good job. My PB is 150. I know. 4.
I could do better. Again, I'm not used to your keyboards, Mike.
Yeah.
Yeah.
Yeah. Well, a sphere is x squared plus y squared plus y squared, and then in 3D a sphere is x squared plus y squared plus z squared equals r squared. So it's more generally is x
X² plus y squared.
x
plus-
x whatever squared.
Yeah.
Define generalization of a sphere in higher dimensional. In higher dimension.
Are you just gonna use general coordinates?
Hmm?
You're just gonna use general coordinates?
For A and
Dimensional, yeah.
Hypersphere defined by. What do you mean general coordinates?
Oh, because I thought you should do 40k specifically. That's fine.
Yeah, just general.
Cannot see. And the reason this happens is because of the angle doubling phenomenon, right? I mean, think about it. As we change this angle up to 180 degrees, the orientation it corresponds to rotates 360 degrees, getting back to where it started. However, the quaternion it's representing has rotated 180 degrees around the hypersphere. In this case, it went from being 1 to being -1. So go ahead and keep playing around a bit if you'd like to build that intuition for which quaternions correspond to which rotations. And in the separate sections, I'll explain why this happens in the broader four-dimensional context of what quaternion multiplication does to a hypersphere.
Okay, one last one. 0. Wow, KJ doesn't know what he's doing.
Yeah.
Oh yeah.
Oh yeah.
KJ is like, how do you multiply a point by quaternion? Oh, you just multiply. KJ, come on. That's interesting.
This is why I use rotation vectors.
Because you just multiply.
You just multiply.
And it's needed because we're gonna forget all of this.
Yeah.
But it's actually, this is cool. Okay.
Yeah, I should definitely review it, I think.
And chunks of text that might follow.
Transformers!
You might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated.
You know, everything you learn,
text, and then
I had to teach myself.
How
do you feel?
Everything.
You're so privileged.
Me? What do you mean?
I had to actually find resources myself.
I mean, I did too.
Oh, didn't you? But you had classes.
I mean, you have classes too.
Yeah, but I never had this kind of class.
I mean, it's in the 4th year course I took. I took a specific course on deep learning.
No, but I'm just saying, like quaternion, and you also learn everything in robotics. I had to self-teach.
I self-taught myself a lot too.
Okay, I respect.
Yeah.
Respect. We're self-learners.
Yeah, but I also then majored in
the
it
whole
too.
process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in the land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved,
Sorry.
then my laptop.
Okay, I have a dinner at 5 now. Okay.
What time is it now?
It's 3:20. We got time. Okay.
What time do you want to call it?
After we finish the 2 deep learning videos.
2?
Yeah, this is part 1 and this is part 2.
Okay.
And then we gotta explain to each other how transformers work.
Okay.
What does the transformer sound?
Like Transformers, robots in disguise. Oh.
Wow. Okay, now.
Text to generate a story based on the seed text. And the story just doesn't, which then seems to is essentially one word at a time when you interact with ChatGPT or any of these other large language models.
But they're not doing next word prediction, right? In Transformers, I thought they would. I guess the general power is probably distribution over the embedding, right? Or over the tokens, embedding tokens. I forgot.
Embedding is basically just like a latent vector. Like you take your thing and then you just convert it into a different space.
And then each element of the embedding is a token.
No, a token is just when you split your text into smaller.
Yeah, like a token could represent a word in half or like half a word, right?
Yeah.
That's the process of tokenization. So after you tokenize it, then you create an embedding from the tokens.
Yeah.
What does the embedding do?
I'm pretty sure the embedding is just you take, like you have some kind of function effectively, and then you take the tokens and then you convert them into a different space, and the network learns the optimal space to represent the tokens in.
Okay, he probably will explain this, right?
Yeah.
Seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models.
What's ChatGPT?
One word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word.
What's the distribution?
It's the probability. It's like you have all your values and you map the probabilities to different values, and you're like, oh, so the whole.
A PDF?
Yeah, like the PDF.
Or PMF?
It's the PDF, not the PMF. Probably mass function.
Yeah, there's probably mass function.
Yeah.
That's for discrete.
Oh yeah, you're right.
Like a Bernoulli distribution, I think it's a PMF, right? No. PDF is for continuous variables.
And then CDF.
That's your cumulative density function. Wow.
Jesus. Let's kick things off with a very high-level preview of how data.
Yo, I did that same animation. That's crazy.
Really? Yeah.
We will spend much more time motivating and interpreting and expanding on the details of
MLPs. Remember when they were just not called MLPs? They were just called neural networks or something?
Yeah, good time.
And then now they call them MLPs for some reason.
I mean, they always did.
They always did call them.
Yeah.
They always called them multi-layered perceptron.
Yeah, but now MLPs is more like.
Just like this simple neural nets are called MLPs, and then transformers, right?
Yeah.
Because a neural net could refer to a transformer.
Yeah.
One of these chatbots generates a given word.
Oh, embedding.
And expanding on the details of each step. But in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood.
The hood. Okay.
The input is broken up into a bunch of little pieces.
Called tokens.
These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound.
That's how they did visual transformers. VIT. Visual. VIT. Visual transformers?
Yeah.
Okay.
Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as
But you need attention to relate their right? That's what attention is for, right?
I thought attention was more for memory.
But like, how do you get the context?
Mm-hmm.
Right, like they could mean different things. So then,
Yeah,
Right.
so attention helps that, I think, because it
So-
represents memory in a sense.
so tokenization literally is just one-to-one mapping. Like no matter where this token is,
Mhm.
it will be the same vector.
Yeah, it should be.
Which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meaning.
And then they got PCA. No.
PCA is not relevant.
Hmm?
PCA is not relevant here, right?
But it's cool. Remember when Google did some PCA where they would like have the words and then you see them in the space.
Mhm.
That's
I
like
don't
they
remember
did the
that.
PCA, right?
Oh.
Oh. T-SNE.
Oh yeah, this is for visualizing latent spaces.
Right? Isn't this PCA or right? Like this stuff, yeah.
I don't fully know how TSNE works, but you can use it to visualize the latent. Like I've used it to visualize the latent space before.
And so on. We can also look close.
This is not related. PCA.
It
back in.
probably is. I just don't know how. I don't know how TSNE works.
Tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values.
Isn't that what I said? Will you say attention is not used for that?
Hmm?
You said attention is not used for the token.
No, it's used to like it's used as memory.
Mm-hmm.
Well, the meaning of the word model in the phrase a machine learning model is different from its meaning.
And
in
yeah,
the
like what
phrase
to
a
pay
mapping
attention
model.
to.
The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated.
Wow.
And again, whenever I use the word meaning, this is some.
What are these vectors? This is from the tokenization process, no?
Mm-hmm.
Why are they different?
Probably because they have different meanings.
But I thought after you tokenize it, it's the same.
I thought these words should be the same, but I guess maybe for per every definition of the word too, they just use a different one.
Word. Contextual embedding.
Oh, I see. I don't know about contextual embeddings.
Yeah, BERT or GPT. So tokenization is just the process of splitting it, and then embedding is a mapping from the token to a vector.
Yeah.
So tokenization is not a mapping from a word to a vector.
Yeah. Yeah. So tokenization. No. So tokenization. Yes. Like the guy said, you split it up and stuff. Embedding is you take that and you convert it into like some kind of vector.
But when you train, like, aren't they like jointly trained, or like, how do you know how to tokenize if you don't have embedding, right? Like, I think
I might be wrong, but I think the tokenization process is probably like a design decision. But the embedding is trained jointly. Yeah.
it's tokenization trained is
But they might even do joint training too. Oh, okay. It could be hard coded. Oh.
sorry. I think like he talked about it here.
Mm.
Yeah, these sides were pretty good, honestly. This is like my first proper intro in class.
Mm.
Transferring sequence to sequence, and then the architecture, tokenizer, tick token, and then a mapping from tokens. A token embedding mapping is trained independently from the LLM. I guess the tokenizer can be just hard coded, right?
Yeah, I don't know what they do nowadays, though. Like, I wonder if like OpenAI, if they actually did hard code the tokens, or if they just like somehow learned it.
For Chat GPT.
Oh yeah, they did. It's just right here. Learned.
Oh. Oh, you see, I really don't know what I'm doing.
I don't either. Don't worry.
See, like if it's just freaking empty like that, it means like never freaking learn what a tokenizer is. Alright, tokenizers, hard coded or the. Let's see how much I know about embedding.
I heard so much. No.
No, I don't know what an embedding is. Oh my god. What a noob.
Don't worry.
Dude, this guy's a noob. This guy is an absolute noob.
I feel like you don't have to like memorize concepts ever though.
But I actually generally don't know what an embedding is, right? So that's why I literally have nothing. So like, it's kind of sad. I can't bullshit people if like you look at my notes and I have nothing on embeddings, and it's like you probably don't know what an embedding is.
Do you think I could do it?
What?
Bullshit.
Well, you already got it wrong. Like I asked you tokenization, and then it's like.
No, I didn't get it wrong.
Oh, so okay, I understood it as you when you explained it. It's a mapping from a token to a vector. Maybe I misinterpreted.
Oh, yeah, I said that was embedding.
And embedding, right? Yeah. Okay, so you did know, but I didn't know.
Yeah, but you can go back on the video and see the proof.
Oh, but you didn't know that embeddings, you could have contextual embeddings. That you didn't.
Yeah,
know.
I know that.
I didn't know that.
I only knew about hard coded ones. Or ecstatic ones.
Oh my god, where's this contextual? What percentage of my notes do you think is AI generated?
Huh?
What percentage of my notes do you think is AI generated?
Maybe. I don't think you actually AI generate that much. Because you usually also write it in your own words after.
Yeah.
So I would say like maybe 40 to 30. Like 30%, 40%.
Is AI generated?
Yeah.
I hope less. Okay, yeah, this is AI generated. But like I rework it. I'm gonna rework it.
Okay. You don't have to justify it.
So far today, like how much have I AI generated? 0.
Yeah, not that much. Yeah.
Well, apart from this note.
Yeah.
And this. TSNE, PCA, Hypersphere, like that was AI generated, but I rewrote it.
Yeah, that's why my guess is like 30% or so.
I actually like didn't AI generate this. This might be copied from a textbook, and then ChatGPT, like I guess when I say ChatGPT, I used to cite ChatGPT.
That's good. That's good. That's a good academic practice.
Or embedding. Depends on.
You won't get sued for copyright like OpenAI.
Like DeepSeek. Is a mapping. Is a mapping from. Tokens to vectors. So the
Now entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the
Yeah,
difference
feed-forward neural network. That was what I called it.
they all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories.
Remember it was RNNs?
Those are the days.
Well, we're bringing back RNNs soon, right?
Maybe.
An initial snippet. To make a tool like
LSTMs.
into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system
I
prompt.
think I went through like a tutorial on Udacity. I think it was Udacity on RNNs. I didn't understand anything. I was like, cool, I understand CUDA, I understand RNNs. And I didn't get a single thing. I was in first year.
You were in first year uni?
Yeah.
I guess I don't know RNNs too then.
Yeah, I just like went on Udacity. I was like, cool, I'm a god now. Even though I didn't understand the
No, it's like, it's this article.
yeah.
They probably use this diagram, right?
I feel like every time someone talks about RNNs, they're like, they just skip it. They're like, oh yeah, like they give you a very surface level understanding. They're like, cool, it makes sense, and then you move on.
Yeah, because you know.
This is actually pretty detailed though, but usually I think people cover it like they're like, oh, you know, like there's like a short-term block and a long-term block or something like that, and it's like, yeah. And I was like, cool, I guess that kind of makes sense. And then stop.
And then you use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with
Dot product.
you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks. Generally considered a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks.
Training and position. Okay, so probably this is a lot of review. So let's
skip up to that point. For broader context, these videos are additions to a mini-series about deep learning, and it's okay if you haven't watched the previous ones. I think you can do it out. At the risk, but before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require something.
Okay, this part we are not learning anything.
We almost take this for granted these days, but
We know that.
machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in deep
We
learning,
learn the
instead,
parameters.
you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then somehow you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior.
Reading this
Right
out.
now, maybe the simplest form of machine learning is
First order
linear
method,
regression, where your
which is
inputs
the
and outputs are
second
each single numbers, something like the square footage of the
second
house
order
price.
method,
What you want is to
which
find the line that best
is
suits the
what
to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept. And the goal of linear regression is to
what's so second order, like the 11 bar my key. Least squares is the second order method, right?
Yeah.
Gradient base is like first order because you're taking the first derivative. And then a Jacobian matrix versus a Jacobians for first order. What's the second one?
Hessian.
Hessian. Good job.
Yeah.
I forgot.
Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing. It's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or...
What happened to GPT-3? No, like it just disappeared.
Isn't that ChatGPT 3? Or sorry, ChatGPT came out as GPT 3.
With 4.0 is GPT-4, no?
Yeah.
Okay, I don't know.
Deep learning describes a class of models that in the last couple of decades have much neural computed. I'd like to just pretend that...
Okay, embedding.
And to determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them, and the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words. These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers.
Word to vec.
But it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much, much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment.
Do you remember how word to vec was trained?
Nope.
No?
Do you remember?
Nope.
Familiar with it. We also call
It's like unsupervised. Or is it? It should be unsupervised, or it's like clustering or something.
Oh, probably was.
You can't supervise it. Like, there's no ground. Like, what's the label? Like,
Yeah.
call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space.
yeah, like you pass it some sentence and then do some clustering and then. Right? Isn't it just PCA then? Like, what are these neat stuff? Or like, right? Because like words can be. Imagine like there are 50,000 words and you like that could be like. We one hot encoded into like 1000, but then you break it down into like a 3-dimensional, or just down to like 3 or 4-dimensional, or like how many dimensions for your column, right? And then you just like try to like
Squeeze it in.
yeah,
Yeah.
and some method like that, and cluster it, and then. But I don't know. But nowadays it's like You probably like mask it, self-supervised method.
Yeah, I wonder if he talks about it.
Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much, much higher dimensional. In GPT-3, they have 12,288 dimensions.
Wow.
And as you'll see, it matters to
You
work
know?
in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice. For the
Hyperpine.
sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example, for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not nearly a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information.
But there's more than one.
And you subtract the embedding of Germany, and you add that to the embedding of Hitler, you get something
Whoa.
to the embedding of Mussolini.
Yo.
It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. Things are space. Visualize power examining, presumably because the weight of the pull up. It's enough to illustrate.
You know, the source of truth is in code. Jensen. What did he use?
The idea.
Glove wiki.
The directions in the
Oh shit. Do you use Conda?
Me? No, I just pip install everything, to be honest. Do you use Conda?
Yeah.
You're pretty dedicated.
Oh, it's just like it's gonna pollute your workspace.
Yeah, or sometimes what I do is I create the Conda using Conda, and then I just pip install everything.
What do you mean, like?
So I do Conda create, but then I just do pip install after I get into the Conda environment.
So what's the point of creating that? You should enter the Conda environment and then pip install.
Yes, I do.
Yeah.
Yeah.
Yeah, and then you install everything. Right?
Yeah.
So that's what you're supposed to do, no?
No, aren't you supposed to actually use like Conda?
Pip install Jensen. Oh, it's which pip? This will be a Conda.
Yeah. I thought you're technically supposed to use like pip, like
Conda install.
Yeah.
But you can't Conda install everything. It's like not all of them are available.
Yeah. Also, good job using Mamba. That's like faster. Conda's so slow, man.
Yeah, Mamba is because I was trying to run ROS on
Oh, like
Mac.
I tried that before too. The Robo.
Flow. No, Robo Fort. No.
Robo Forge, I think.
Robo Stack.
Oh yeah, and
then yeah,
that's very. Slow.
I do have ROS. Oh. Ready? I'll be slow, but yeah.
Yeah. Nice.
Yeah, I can ROS to run. Shit, I don't even know. Demo. Talker. To run demo. Oh my god. How do I know my commands?
I don't know. Damn.
Am I cracked like that? Damn.
Damn.
And then you can do Conda activate ROS-env.
Are you gonna run listener now?
Yeah.
Whoa.
ROS
You
to
cheated, don't you?
what?
I thought I said you could search for something.
I heard. See,
Yeah.
pub sub in 2 seconds. Okay, while we're installing, we're gonna keep watching the video.
That's
Oh,
right.
it's ready. Okay, and then Python in the huh? Okay, so
Very classic mind, especially for the next chapter, is how the dot product of two vectors, Italy, when you subtract the embedded.
measure their similarity. Is that what he's gonna say?
Probably, yeah.
Why?
Because dot product tells you if two things are parallel as well, right?
Yeah, if they're parallel, so the the smaller the value, the closer.
They are, yeah.
Right, but how does that? Yeah, because if they're orthogonal, it's no. If they're orthogonal, dot product is 0. So it's actually the bigger the number, the closer.
Yeah. Wait.
Right. The dot product of two perpendicular vectors is 0.
Yeah.
And two perpendicular ones are not very similar.
And for two ones that are the same.
The cos of theta is 1.
Yeah.
So and then the larger there. But the magnitudes also play a role, or is it?
Huh?
Do the magnitudes play a role? Because it's magnitude of A times magnitude of B.
No, but if you if you
Germany, and then you add that to the embedding of Hitler,
I guess
you
they
come
do.
very close to the
But I thought there's a way of showing that it doesn't matter.
embedding of
Go see.
Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders, and you add it to sushi, you end up very close to bratwurst.
Bratwurst.
Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results, which is good since
You know, there's a instruction. There's an instruction at an assembly level or like on hardware.
To do a dot product? I didn't know that. I thought it's up to matrix math. Oh, is this the what's it called again? The SIMD instructions?
Mm-hmm.
Mm.
Yeah. Well, there's this one. This one is like you have a bunch of them, and then there's two, and then the one is like you have 3 registers, and then you store it into a 4th register.
Yeah.
And there's another one is like an accumulator that just accumulates the dot products. So I think there's multiply add, and then there's multiply accumulate. Okay. Python. Oh, that's our.
Yeah, that's the result.
All right, then you do some exploration now.
Sure, I guess I'll do the.
Or like get the distances as he did.
Yeah, I'll do the gender exploration.
What are you doing? Oh, okay. Numpire.
What?
Why are you typing like a noob right now? why are you typing like a noob? Okay, comment out the other thing.
Okay. I guess import empire. And then how do you do?
I think they're already numpy.
Oh, okay, let's just do numpy. There's a numpy dot, right?
Sure. Maybe. Oh my god. KJ, why are you doing that? Why are you using your arrow key? KJ, are you trolling me?
Dude, this is how long
How long you haven't coded for?
Yeah.
KJ, just like go to the end, like capital A, and then.
Will this even work?
Yeah, go. Go on. So what are we expecting here?
I guess 5.
The dot product of those two vectors is 5.
Yeah, and then that's...
You don't even need the square root. Why are you taking the square root of the dot product?
Yes, you're right. I mean, it was just to show...
You're not getting the Euclidean distance. So you didn't. If you did the sum of squared. And then like uncle and aunt.
Yeah. Wait, what's this even gonna show though? Because this doesn't show his point.
Yeah, you should rather compute the vector and then see that the vector is very similar.
Yeah.
Alright, get out of here. Get out. KJ, don't do this.
I know.
Do this.
Okay. Whoa.
Alright. And this is uncle. It's gonna be a bit hard to read, but okay, yeah, I don't know how we're so he reduced it down to 3 dimensions.
Yeah, how do you do that?
Some PCA.
Oh.
I mean, I did this for like the poker. I did this for poker.
Oh, really?
Basically, like,
I
imagine.
thought poker's classical method.
No, I had to do this reduction in poker.
Mhm.
Because, what was it? In poker, you have. Oh, yeah, you have like a bunch of combinations, right?
Mhm.
Like a bunch of cases. And it's like if you teach the AI to like handle all these cases, it's too much. So you can group like similar scenarios together. So instead of like in the pre-flop, you have 169, I think, different combinations that you can reduce it down. But then afterwards, like, your so I wait, there's like equity and equity distribution. Yeah, that's how like you calculate basically like for a given a hand and what you see on the board, like what's your equity, like how that means like if you just do random rollouts, how often do you win this hand, how often you tie, right? But so you can represent it with one number, or you can do it in like 3 numbers, where it's like you sample and then you bucket it. So that's how I did it, but I didn't need to do PCA actually. I did k-means clustering. How did I do k-means clustering? Oh yeah, then it's like you have all these distributions and then you cluster. You assign buckets to like distribution belongs to this bucket because there's like two.
K-means work again? I don't remember anymore.
K-means is you, let's say for 2-dimensional data, you have XY, right? You have a bunch of XY points, and you decide, okay, like there's a parameter for how many centroids you want. So you initialize, say, like 5 centroids. You want 5 clusters. So there'll be like random points, and then in the first iteration, you will each of these points you will assign them to the closest centroid, right? So then there's a group for the first centroid, there's a group of points. For the second centroid, there's a group of points, etc. And then on the update step, what you'll do is like you'll recompute the centroids. So you'll take the average of all these points, and then you'll compute a new centroid. And at some point, like the centroids will stop moving. And during the steps, yeah, like some of the points will be assigned to another centroid, and then like things will shift around until at some point it will stabilize. And that's like your optimal like
solution, I guess. Yeah.
But sometimes like where you initialize the centroid is pretty important, right? So there are like variations where you can like try a bunch of different centroids until like the one with the like least error will be chosen as like the best centroid choices. And then there's like methods like, oh, how many centroids do you determine? You can try, like I actually did this analysis of how many centroids to try. And the only reason that I now know why k-means is because Zutang was asking me how k-means worked, and I was like, oh, it's not.
Who did?
Zutang.
Oh, from work?
Yeah, because she was interviewing candidates, and she was like, yo, Steven, can you explain k-means?
Anyway.
I was like, oh, it's easy. And then I was like, oh, shit, I don't know. So now I remember.
Oh, nice.
Yeah.
You're like trivial, and then...
Huh? It's trivial. So she asked you, you'd fail too.
She didn't ask me.
Yeah, she asked some candidate.
The dot product is positive when vectors point in similar directions. It's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model, and you hypothesized that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values.
What's happening?
So as if we can
I think, so basically what he's trying to justify is that there's this notion of plurality. And so he's showing that if you take the dot product between octopus and octopi, for example, or cat and cats, the lower values tend to be they're a dot product. I don't know what the plural vector means though.
That's the difference between cat and cat.
Oh, okay, I see. So he takes this plural vector, and he shows that things that are plural, so similar to like octopus and like octopi dot plural, for example,
are more similar
compared to octopus dot plural. So it's to show that there's this notion of a plural vector.
Yeah. And it's more similar to things that are actually plural versus things that are not plural.
Yeah, exactly.
We measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257. And again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those,
We're
our
such
world
nerds,
consists of
bro.
about 617 million weights. Let's go
I
ahead
love
and
it.
add this to a running tally, remembering that
But
again,
you're gonna
this
stop
is
grinding soon.
75 billion.
Dude, I want like vacation.
In the case of transformers, you
This
can
is our
define
vacation.
specific
Isn't this pretty chill? Like, would you rather watch this or watch a movie?
Depends on the
movie. Yeah.
Depends on the mood.
Oh, depends on your mood, not the movie.
Yeah, it depends on the mood. And the movie.
Are you in the mood right now?
Yeah, sure.
He's not in the mood, guys. I forced him to be here. What would you rather do, bro?
Or sleep. I think I told you when I woke up. I told you I got like not a good sleep. That was a good sleeping.
Yo, I woke you up at 10.
Dude, 10 a.m. so early.
10:30.
10:30 so early.
I have to get to work at 9 or 9:30 every day.
I do too.
It's always 10 early.
I think I'll get fired one day. I don't have a meeting at 9 anymore. You know they don't have stand up at 9 anymore.
Yeah, I know, because it's so early.
Huh?
Yeah,
Yeah,
it's
it
too
changed my world for the worst.
Wait, what time do you guys get dinner?
Huh?
What time do you get lunch, sorry? Lunch?
12.
At 12, right? I get lunch at 11:30 now.
Really?
Yeah.
Damn, good job.
Multiplying those,
Earlier,
that
earlier
consists
lunch.
of about 617 million weights. Let's go ahead and add this to a running tally.
I miss eating lunch with the team, though. I think, like, we had a pretty good dynamic.
You come, stop by.
Stop by?
Yeah, stop by one day. I can invite you. I can let you in.
No, actually, but I can't. I have work too, you know?
Oh, can't you like tell? I guess could you like tell them I wanna?
Meet a friend?
Yeah.
Just for lunch?
Yeah. You can come in for lunch and then dip.
Yeah.
Like, obviously, you can't stay the whole day because I'm assuming they'll be pissed off, right?
Yeah.
But you can come in for lunch, or like, you know, you can like ask them, hey, can I like disappear?
Yeah.
I don't know
probably
how strict they are with monitoring.
It's kind of weird too. Like,
Mhm.
I ran an intern at Tesla and then just like coming for lunch at NVIDIA.
Yeah.
We should count up to 175.
You guys are getting trade secrets.
Yeah.
In the case of transformers, you really want to.
I'm joking, by the way.
It's actually.
Mhm.
Okay, I won't say this on camera. Okay, we didn't say anything top secret.
Space is not merely representing
We can say it on camera too. No, we don't need to say it.
individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example,
Yes,
might
king.
progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words can represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details
Because
of
why?
attention. Constant network
Because the
is
context
going to
window is
use each
limited.
one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent.
But this, I'm a little confused. So this process, this is just the embedding, no, or is this like the attention?
He's
This-
just showing embedding still.
This is just embedding.
However,
Yeah.
this includes context from a long distance away.
He's trying to basically explain why context embeddings exist, or whatever.
Yeah, contextual embeddings. But when you look at the word itself, it's sort of like the meaning of this word within the context. How does the contextual embedding get computed though?
I don't know. I'm assuming he'll explain that.
So in putting together a model that has the ability to predict what word comes in a text, when the primary goal and of the time, known as its within the text stuff. I'll leave a conversation for a minute about what happens at the very. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding we see least favorite teacher, and also be giving some leeway by letting me pretend the tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word snake. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with snake. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a thread of conversation as you
I was on
continue
that
to
one.
We'll go into the details of it
403.
time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words
You know
like Harry
Cohere?
Potter,
Yeah.
Yeah.
Who are the co-founders?
I know they're all U of T alumni. One guy was the guy on the Transformer paper.
Hayden Gomez. Yeah.
Maybe Gomez. I don't know the rest.
And then there's Ivan.
Mhm.
And the funny story with Ivan was like, yeah, I met him like Hack Western, and at the time I was just like, didn't know. Yeah, you see, I still don't know what embedding and tokens was. But that was like 2 years ago, and I just went up to him and was like, yo, explain tokens and embeddings to me, bro. Yeah, I was kind of like a naive, like arrogant kid.
and
But it worked out, I
immediately
guess.
we see least favorite
I
teacher,
did it. I
and
don't
also
know.
begins
I still don't
to
know what
the
embedding
tokens
is
simply look like full
until.
Oh, you mean you?
Then a
Me, yeah.
You went up to them?
knowledge of
No, you
Wait.
meant that's how they met.
Oh, no, that's how I met them 2 years ago.
Hey, what happened?
No, nothing really.
Do you think you're a genius?
No, the thing I was stupid.
Another matrix that
It's
maps
okay.
the last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that
Question
in
for
training
softmax.
Mhm.
Does it, like, okay, between 1 and 2, it makes it so that 2 becomes much larger, right?
Mm-hmm.
So enlarge the differences. But what about the negative numbers? Does it also enlarge the differences? I guess, like, do the negative numbers,
No,
a
because
more negative number, does it get more? No.
what's e to negative 0? What's e to negative 100?
Pretty much 0. Pretty
What?
much 1. Pretty much 1, yeah.
Yeah, so there's no 1. No,
Or no,
0.
1 over, oh,
It's
0,
0.
0, sorry. I'm so stupid, sorry.
It's 0. So what's e to negative 200?
Or something that's even more 0?
But the problem
Closer
is
to
the
0.
relative difference between something that's super 0 and something else that's super 0 isn't big, right?
Yeah.
So that's why softmax can't handle negative numbers well. Is because when the numbers are super negative, they're like,
There's no difference.
yeah, there's no difference.
Okay.
So it doesn't do good on negative numbers.
But at least okay.
Mm.
Which way you batch normal?
Huh?
Which way you batch normalize it? So you
I don't think batch normalization will fix that issue with it. Because just with the output velocity layers, so I don't know how.
Because remember the activation function, it's really effective at like there's only a range within which it's effective, right? Like
Yeah.
even ReLU,
you
ReLU.
don't, you don't use batch norm on your loss layer either, right? Or do you? You don't. Yeah, you don't. Because Yeah, I know Batch norm is a bit controversial too because it shifts the distribution of the data to be Gaussian too, if I'm not mistaken. Because you give it meaning.
Like from what I remember, the point of Gauss norm is like your activation function like will be oversaturated or like after for super positive values or super negative values, right? So you want it to like always sort of stay between -1 and 1, right? And so if the number is here, you sort of like renormalize it to be within this range so that it's the gradient of that is sort of effective. I see it. Yeah.
Yeah.
Can't explain it super well, but that's sort of the intuition.
Yeah, but I don't know if that will bound the outputs of the the final output. So yeah.
Process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each.
Wait, what? Unembedding matrix.
Yeah, I kind of lost track as well.
To the word snake. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each.
This is the prediction. And so you predict some vector and then you need to, this is maybe some word and then you multiply it by this. This is an unembedding or this is
unembedding matrix.
Yeah.
Then there's a function that normalizes this into a probability.
And you softmax and then you take the
softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over 1 billion. A small, but not wholly...
You never learned about the unembedding matrix, did you?
I don't think I did.
So when I was learning transformer, right? So they say like the embedding matrix is trained separately from the LLM. So what about the unembedding matrix? Is that also trained? Like, is that trained with?
Presumably, it's not trained with the network. Or it would actually. Yeah, you can ask.
What? Oh, I guess this is the token. Bruh.
I have no comment.
The embedding trained.
Oh yeah, I think Orange Karparthi has like a 0 to hero. I haven't watched the series, have you?
Yep, I have, but not everything.
Oh.
So embeddings are also jointly trained. That means my teacher doesn't know what he's doing.
It also could just be that the teacher taught you like the
GPT-2.
Yeah.
Yeah, I asked like a follow-up on tokenizers, and he's like, "Yeah, I don't know. That's not my field of expertise."
Yeah. So I can relate. I don't know anything about this. It's pretend I do.
As the very last mini lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, The outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is a standard way to turn an arbitrary list of numbers.
In a PDF, you don't need the numbers can be greater than 1.
Yeah.
As long as the area under the curve
Integral,
is 1. Yeah, because imagine if it's like range from 0 to 0.5. Then
Yeah, but
the
this
area
is
equals to-
this is like
So-
the final probability values. This is not PDF. This is like PMF, whatever.
Into a valid
It's like the
distribution
mass function
means that
almost.
the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term.
Why
by that
E
sum.
though? Why not 2? Why not 3?
That's actually a good question.
I'm like, I asked such a great question.
Yeah, you're a god.
Without ChatGPT, I would like not know.
Yeah.
But ChatGPT has the answer to all my questions. What?
Higher IQ than both of us combined.
Why do we use a softmax? When we use a softmax, we use E. Why do we use E? Why not 2 or it's 5 to the x
Or 10.
or 10? Oh, because the derivative.
Oh, it makes.
But derivative of 2 to the x is 2 to the x.
Huh? No, it's 2x
ln
x. 2 ln 2.
Oh, you just
Oh, also log sum trick. Go down. I forgot about this completely.
You know this?
It's been a long time, but yeah.
Dude, you're that old, bro.
Huh?
You're that old?
Yeah. Real softmax, damn.
Fuck. We're going soon. Okay, I know you're tired, bro. But you're gonna grind with JBers today.
Nah, maybe not. My tone today's not the day.
Cause I overworked you. That is pathetic, KJ. If I overworked you, if this is overworking.
I'm so old. My brain's like, I'm already like peak.
You think if you asked your professors, none of them would be able to explain it to you?
No, they would be able to explain to me.
Exactly. So if you want to be a professor, you need to know it.
Yeah, I know. I peaked. I feel like I just need to get sleep.
So what's the log sum x between? I don't know.
So it's just the idea that, if I remember correctly, just the idea that if you have, so you know the log rules?
Mm-hmm.
So if you go here.
Log of a times b equals log a plus b. Log a plus log b.
Yeah. So these log rules, log a plus log b. So then if you have, if I remember correctly.
But this is log of a plus b
let's
plus
just do
c.
this.
It's control. It's command. You have to use command, not control. Command C. We did option R. Yeah, okay. No, you really haven't coded. No, it's the key over, right?
Yes. Yeah.
Numerical instability? What does that mean?
So basically, if the numbers are too big, you might get like nans and stuff, or the computer can't represent it.
No, but you just do infinity. It wouldn't be nan, it would be infinity. I guess it's like
Yeah, it might be
Implications
infinity.
or
Yeah, but basically it triggers like a.
nan happens
floating
when
point,
you
right?
multiply a 0 by infinity.
Oh, okay. But yeah, it's like a floating point full or something like that, right? Like, you can't represent it anymore, so that's why.
There's so much to learn. Holy crap. If you know everything, you know nothing.
Mm.
But I feel like you look at like any like you look at Dieter Fox, he probably knows everything we know
And more.
and more, right? So that he just actually knows everything,
Mm.
right?
I guess so. That's why I asked to be under him. Never heard.
But maybe we're overhyping him. Okay, I feel like I think I need to drag it back. All right. What do you think is the commute back to your place?
Hmm?
What's your address? What? You want me to lift you?
That doesn't matter.
Doesn't matter. That doesn't matter. With my friend, could you add me?
That's fine too.
That's fine.
which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's
Because of the log x trick. What the okay. Where the fuck did the M come from? Oh. Log of what? Sum of I equals 1 to n of e to the xi is equal to m plus log I equals 1 to the n e to the Is that right?
Looks right. Here, you should ask. Here. Yeah, now you know.
in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature.
Whoa,
in
you know
certain
this?
equations.
I don't know about
And the
this.
effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform. And if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value.
Oh
For
my
example, I'll
god.
have GPT-3 generate a story with the seed text, once upon a time there was a, but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature.
This feels like, you know, in RL,
Mm-hmm.
you
Exploitation versus exploration.
or like
Like you randomly sample an action.
yeah,
From-
you always take the argmax or you take like an epsilon greedy.
Mm.
Right. Yeah, like if you want max exploitation, you just always take the max.
Yeah.
But if you want some exploration, you can do the simplest is like epsilon greedy, where you have a probability of taking random action, else you take the max. And then what are the other ones? UCB, upper confidence bound, and there's Thompson sampling. You know that?
Nope.
You don't know that. I actually did this at Ericsson.
No.
So it's the multi-arm bandit problem.
I've heard of that before, but I'm not too familiar with it.
Yeah, but it's like the most primitive form of like the exploration versus
Mhm.
exploitation problem. Like you imagine like you have a bunch of slot machines,
Mhm.
and you're like, oh, which slot machine should I use? Right?
Mhm.
But the slot machine doesn't have a guarantee of like giving the same reward every time. So it's
Yeah.
like, which slot machine do you all play? Like maybe you play it once and like that slot machine gives you the most, but it's like maybe next time, maybe this one like, oh, just like you were unlucky. So it's like, how do you determine which slot machine to play?
Yeah.
So that's like multi-arm bandit. Cool.
Gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits. Or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter
Oh, really?
is to lay the
Lodge is the unnormalized one? I thought Lodge was. Oh, yeah.
the foundations for understanding the attention mechanism. Karate Kid wax on my soft style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters,
This is cool.
then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. Up to the path with a constant GPT for than just picking the math.
Ruby would be so smart. It's like insane.
He went to Stanford, yeah?
Oh, Oh, that's probably why.
It's just like e to the x over t. You use e to the x over t. T. Okay, we should go soon. But what is this kt thing then? I saw kt.
K is
Is the-
either 1 or a constant. Or the Boltzmann constant. The Boltzmann constant is insane. I remember like this in like
Wait, isn't this from chemistry?
yeah.
What? That is crazy.
I think they're just using it for fun though.
Just for fun.
Yeah.
I agree with you.
PV equals nRT.
Where's the constant?
PV equals nKT. And R is the constant. Yeah, R over NA. Or N R over N. Yeah.
What is this called? PV equals nRT?
That's the ideal gas law.
Damn, I have no chem notes.
Damn.
I'm washed.
You're cooked, yeah.
Oh no, I have. Ideal gas law, is that what it's called?
Yeah.
Are you sure?
Yeah. PV equals nRT. Or, but R, but yeah.
Can you do that? Isn't that cool? Multi-line insert.
Yeah, you're so good. And also then R, the ideal gas constant, we convert into the Boltzmann constant. But it's not the Boltzmann constant. It just can be converted into it.
Right. Gas. Avocado? Did I see avocado? Avogadro.
Yeah, avocado. Avocado.
Oh my god, this is bringing back memories.
I know.
How this is like when you used to have dreams.
Distribution is a little bit more uniform.
Before my soul crashed my corporate life. Joking.
This is one of the key pieces of technology that our business models and a lot of other pieces in the modern way.
We're joking, guys. We're joking.
In a now famous 2017 paper called "Attention is All You Need," and in this chapter, you and I will dig into.
Oh shit! Okay. Fuck. This is like the most fundamental thing.
Yeah.
But I think it was a good review. Because you don't know how attention works, right?
Yeah.
Yeah, well, we'll continue attention. I think, yeah, we're learning a lot of things today. Okay, alright. I'll see you guys later. Bye-bye.
Bye.